Polynomial functions have the form p of x. Oops, let me just make this a very thin pen. P of x is equal to a naught plus a1 x to the power of 1 plus a2 x to the power of 2 plus and so on all the way up to a n x to the power of n. Now this is not something new for you. This is something you would have seen previously before. And you've seen a number of functions, and I'm going to express them in the same way. I'm going to say, let's call a function q of x, right? And you've seen a function q of x, and that function looks something like this, in which we have a naught plus a1 x to the power of 1. This is exactly the same as saying something a plus bx. And very commonly, that's exactly the same as saying it is mx plus c. Okay, and so there you go. That's your first hint. This is all the exact same polynomial. What are these a naughts, a1, a2, all up the way to an? What does that represent? Well, the reality is a naught, a1, all the way up to an. Each of these things are just simply coefficients, right? And those are real numbers. So I'm just going to put there, those are the coefficients, right? And so now from this, you can automatically tell me what's the next polynomial you've already seen. Well, that polynomial looks something like this. If we express it algebraically, let's call it q of x again. And we could say that polynomial is actually a naught plus a1 x to the power of 1 plus a2 x to the power of 2. And the reason each of these a naught, a1, a2, they're all just coefficients, right? And I represent them with different numbers simply to indicate that the coefficients themselves are different. This is exactly the equivalent of saying it's c plus, or rather let's just leave it as a's, a plus bx plus cx squared. Right? Now very commonly, I'm not going to use the exact same one. I'm going to say that format is actually just a quadratic function. It's just a parabola. And if you turn it around, remember that in South African curriculum, you commonly see a function being expressed as ax squared plus bx to the power of 1 plus c. And here your coefficients are just a, b, and c, and over here they are just a naught, a1, and a2. And really this is a polynomial function. Now, I want to compare a few polynomials, and I want you to tell me something about them, right? I'm going to give you a linear polynomial. And a linear polynomial is just polynomial of the form ax plus b or mx plus c. And that means that it's going to have what we call degree 1. So this is the first polynomial, ax plus b. The second one is going to be ax squared plus bx plus c. The next one is going to be ax cubed plus bx squared plus cx plus d, right? And then you can imagine what the next one would be, ax to the power of 4 plus bx to the power of 3 plus cx to the power of 2 plus dx plus e. And each of these have got different names. The first one over here is going to be called a linear polynomial. It means it has degree 1. This is called a quadratic polynomial. This is called a cubic polynomial. And this over here is called a quartic polynomial. Now I'm going to put something on the side over here that shows you a visual graphical representation of each of these polynomials, right? And then that is a linear polynomial. This over here is a quadratic, which could look like that or could look like that. A cubic would look like this, right? And a quartic, I'm going to give you a quartic function, right? Would look like that. Now I want you to take a minute and tell me, what do you think the relationship is between what we call the degree if you look over here, what's the relationship between the degree, which is power of 1 over there, this is to the power of 2, this is the power of 3, this is the power of 4. What is the relationship between the degree, in other words, the highest or the leading exponent, and the number of turning points that you see over here? What can you tell me? Take a minute, explore it, study the turning points. The turning points occur over here, or over here for this one. Turning points over here and over here for this one. Turning points for this one over there, over there, over there. That's the number of concavity changes, or the turning points, right? Okay, so if you've got it, I expect you to notice that the linear polynomial has highest power exponent 1, but it has 0 turning points. A quadratic polynomial has got 2, has leading exponent of 2, the highest power is 2, and the number of turning points is only 1. The cubic polynomial has 3, and the number of turning points are only 2, and a quartic polynomial has 1, 2, 3 turning points, with the highest degree being 4. So what is the relationship essentially between the turning points and the degree of the polynomial? The degree is always 1 more than the number of turning points when we represent that function graphically, or the turning points are always 1 less than the degree of the cubic polynomial, okay, or rather of any polynomial. So that's a basic introduction to the polynomials. Remember the form they must have. There must be a coefficient, a variable, and an exponent. Coefficient, variable, and exponent. Coefficient, variable, exponent. Over here we also have a variable. The variable is x, and the exponent is the power of 0, because x to the power of 0 is equal to 1. So it's cx to the power of 0. And that's really what a polynomial function looks like, right? Let's go back, and here we've seen a0 plus a1 x to the 1 plus a2 x to the power of 2, a plus bx plus cx squared, or as you commonly would have it with your coefficients being ax squared plus bx plus c. And that's the format of the polynomial functions, right? There's one thing I didn't mention to you. These numbers over here need to be real numbers because we're studying real polynomial functions, and the exponents must be elements of the natural numbers. So the exponents, in other words, n, right? The exponents n must be an element of the natural numbers, right? So in other words, you can't have fractional or rational exponents, then they're not considered polynomial functions. They're really functions of a different format, and we're going to discuss each of those in a bit more detail in the future.